Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET, Jest, TIFR, IIT-Jam and other exams related to physical science. Okay, so this is the lecture number 21 of mathematical physics, in which I'm going to discuss Hermite for Hermite differential equation, Bessel, uh, uh, Laguerre differential equation, and Euler differential equation. Okay, and before starting the class, I would request the people who haven't subscribed my channel yet, please subscribe my channel and watch my lectures, free live lectures, which are going to help you to crack the exams related to physical science. Okay, so I'm going to start now. I will start with Hermite differential equation. Okay, okay, just meanwhile, let me just check, am I audible or not? That is important. Lectures which are going to help. Yeah, yes, I'm audible. Okay, so I'm going to start. So Hermite differential equation. Okay, we have already studied legendary differential equation in my previous lecture, so you can check it. Okay, so 20 lectures have been completed for mathematical physics, so you can check that. Okay, so Hermite differential equation. Okay, so the form of Hermite differential equation is d2y over dx, d2y over dx square minus 2x dy over dx plus 2ny equal to 0. Okay, so d2y over dx square minus 2x dy over dx plus 2ny equal to 0. Okay, so this is the Hermite polynomial. Okay, sorry, Hermite differential equation. Okay, so we'll check at x equal to 0 is ordinary point or singular point for this equation. Okay, so we can see x equal to 0 is ordinary point. Ordinary point. How? Because we from here we can see px is 2x and qx is 2n, right? Qx is 2n. So we can find this one like limit x tend to 0, px equal to limit x tends to 0, px value is 2x. If you put the value here, 2 into 0, that is 0. And for qx limit, limit x tends to 0, qx value, that is going to be 2n, right? So we can see finite value. So x equal to 0 is ordinary point for Hermite differential equation, which is in this form. Okay, d2y over dx square minus 2x dy over dx plus 2ny, okay, equal to 0. Now we'll find Rodriguez formula. Okay, Rodriguez formula, that is Rodriguez formula. Rodriguez formula. Okay, so Rodriguez formula for Hermite polynomial it is Hn x is going to be this is minus 1 to the power n minus 1 to the power n e to the power x square dn upon dxn e to the power minus x square. Very important, guys, because Hermite polynomial also I have explained in quantum mechanics, okay, in harmonic oscillator chapter, because this is important. Okay, so this is Hn(x) values of Hn1, Hn0, Hn2 that I have already explained in my quantum mechanics lectures. Okay, so here also I will write those things for you. So this is the Rodriguez formula. Okay, minus 1 to the power n e to the power x squared dn upon dxn e to the power minus x squared. That is the Rodriguez formula. Okay, so, okay, yes. Now these so we can easily find out from this from Rodriguez formula h1 h0x h0x, okay, which I have also explained in my quantum mechanics lecture, that is for quantum harmonic oscillator. Okay, so h0x is going to be for n equal to 0. Okay, so h0x values is 1. Okay, and this and h10 h1x, okay, h1x value is 2x. Okay, and h2x value is h2x value is 4x square minus 2, and h3x value is this is 12x cube minus 8x. Okay, 12x sorry, my apology, this is not correct. This is 8x cube minus 12x. Okay, 8x cube minus 12x, 8x cube minus 12x. Okay, 4x square minus 2 is 4. So these polynomials are very important, so you need to note down these and memorize it, guys, because if you know these polynomials, right, these values, you can easily solve a question very quickly, okay, in the examinations. So very important. And this these values also I have explained in my quantum mechanics lecture. So h01 value is 1, h1x value is 2x, h2x value is 4x square minus 2, and h3x value is 8x cube minus 12. Okay, well, this is so there is a property, and the property of Hermite polynomial is Hnx Hn minus x. Okay, Hn minus x value is minus 1 to the power n. Okay, I'll write it in next page. Very important property, right? So this is Hn minus x. Okay, Hn minus x, this value is minus 1 to the power n Hnx. Okay, so if we have been given Hn minus x, so we can easily convert this Hnx. Okay, and this is Hn minus x is minus 1 to the power n Hnx. Okay, and this is even for even n and odd for odd n. This is even for even n, even for even n, and odd for odd n, odd for odd n. Okay, they are very important thing. You need to memorize it, guys. Then you can easily solve questions. Okay, now generating that is orthogonal condition for this Hermite differential equation. Okay, orthogonal condition. Orthogonal condition. Okay, there are five differential equations. These are Hermite, Bessel, Legendre, Laguerre, and Euler. Okay, Cauchy-Euler differential equation. Okay, so orthogonal condition is this is integration minus infinity to plus infinity e to the power minus x square hmx into Hnx dx is equal to 2 to the power n. So integration minus infinity to plus infinity e to the power minus x square into hmx into hnx dx is going to be equal to 2 to the power n into n factorial root pi n factorial root pi chronicle delta mn. Okay, so delta chronicle delta mn equal to 1 if m equal to n. Okay, 1 if m equal to n, and chronicle delta mn equal to 0 if m not equal to n. Okay, so this is the orthogonal condition. Okay, well, next is generating function. Generating function. Generating function. Generating function. Okay, so generating function is, this is gxt. Gxt is equal to e to the power 2xt minus t square, e to the power 2xt minus t square. Okay, so this is the generating function, and that is equal to sigma n equal to 0 to infinity t to the power n hnx upon n factorial. Okay, this you will get in your question also. Okay, so gxt is equal to e to the power 2xt minus t square, and that is equal to sigma n equal to 0 to infinity t to the power n hnx upon n factorial. Okay, now we'll find the value of this one, sigma n equal to 0 to infinity. So this value is going to be here in this equation, right? So we'll put x equal to 0 in this expression. So e to the power, so this is going to be e to the power 2 into 0 into t minus t square, right? And this value is going to be e to the power minus t square, right? So this is going to be sigma hn0 t to the power n upon n factorial, or we are doing n factorial is going to be, we'll open this, right? We know how to open e to the power x. So this is 1 minus t square plus t to the power 4 upon 2 factorial plus 1, right? We know this e to the power x 1 plus e to the power x plus e to the power 2x upon 2 factorial, right? This we know. Sorry, my apologies. So this is 1 plus e to the power x equal to 1 plus x square by 2 factorial plus x to the power 4 factorial. Okay, so this is, we have used this formula. So now, so this is going to be, so this is the one, right? Now we can easily find like value of h30 upon 3 factorial, right? T cube, we can easily found from here, right? Here you can see there is no t cube term, right? So this is going to be 0. That means h30 value is going to be 0, right? 0. So we can easily open it and we can find any value, whatever value is asked. Similarly, if we have to find this one, coefficient of h31. Okay, we have to find coefficient of s31. Okay, s31. So what we'll do, this we know, sigma x equal to 1, okay, h31 t to the power s31, right, s31 we need to find, so and t cube, right, t cube upon 3 factorial, okay. For this we need to find h1 s31, okay, s31, so yes, s31. So this how we are going to get it? This is hn, okay, hn1, hn1 upon n factorial. So we need to find out that value of hn1, okay. For that, what we'll do, we know this value is e to the power minus 2tx, right, 2t 2tx 2tx value is 1, where for x equal to 1, right. So 1 minus t square, right. So this is going to be e to the power 2t minus t square. We'll open it. So this is going to be sigma hn1. So hn1 value we need to find out, okay, hn1, so not h3, this is hn1, hn1 hn1 value we need to find out, okay. So hn1 for this coefficient of hn1, okay, t cube going to be n factorial, and this will open it. So if we this vector we know how to open it, right. 1 plus 2t minus t square plus 4t this whole square, right. We'll open it. 4t minus t4 minus t cube 4t cube upon 3 factorial plus 2t minus t square whole cube upon 3 factorial plus so on, okay. This is the one, this t cube, okay. Next is going to be then we'll find the coefficient. So h, yes, we have to find out h31, guys, h31, okay. h31, this is going to be s31 upon 3 factorial is going to be minus 4t, only t cube term will take, okay, upon 2 factorial plus 8 t cube upon 3 factorial, right. Here we'll just take t cube term only, okay, this one t cube term, here also t cube, just t cube term. Four upon 2 factorial plus 8 upon 3 factorial, 3 will go here in 3 factorial, right. So this value is going to be minus 4 into 3 factorial upon 2 factorial plus 8 into 3 factorial upon 3 factorial, and if we solve it, and this is going to be minus 12 plus 8, and that is minus 4, right. This is how we'll solve, we'll find the value of s31. So this is a lengthy process, right. As I told you, if we know these values, if you know these values, that these one h10 h2 h10x h1x, this one h0x h2x h1x h3x, then we can easily solve it, okay. How? I'll tell you. So for the same case, okay, for the same case we need to find out h31, okay, h31 we need to find out. So we can, how easily we can find out now, since we know hnx means s3x value, right. We know s3x value, we know that is 8x cube minus 12x, right? So from here h31 is going to be very simple. We'll replace x by 1, so 8 into 1 cube minus 12 into 1, right? 8 minus 12, that is minus 4. How quickly we have solved it, right? So if you know those terms, right? So I would request you just practice questions and memorize these terms, okay? Because these are going to help you a lot, and you can easily solve questions in your examination. So it will not waste your time, okay? Well, so this is the one. Next is uh, that is Bessel function, okay? So this is the second method, okay? We can say direct method. Direct method. Okay, so how quickly we have solved it, right? Next is Bessel function. Bessel function, okay? Bessel function. So Bessel function. So first we'll write the equation of Bessel function. This is x square d2y over dx square plus x dy over dx, okay, plus x square minus n square y equal to 0. Okay, so x square d2y over dx square plus x dy over dx plus x square minus n square y equal to 0. Okay, so this is the form of Bessel function. Okay, sorry, Bessel differential equation. My apology. It's Bessel. It is Bessel differential equation. Okay, Bessel differential equation. Well, so we'll solve it further. So this is going to be d2x upon dx square upon 1 upon x dy over dx plus x square minus n square uh, upon x y equal to 0. Okay, so from here px value is 1 upon x and qx value is x square minus n square upon x. Okay, so we'll check at x equal to 0. We'll check limit uh, x tends to 0 px. So this is giving infinity value, and similarly limit x tends to 0 qx. Qx is also giving infinity value. Right, we'll write put value here. So 0 minus n square upon infinity 0, right? And 1 upon 0 is this is 0. This is going to be infinity. So we can see at x equal to 0, value of px and qx both are infinity. It means x equal to 0 is regular singular point. Okay, x equal to 0, regular singular point. Next. So now solution of Bessel function, which it's very important. This question is asked in CSIR NET June 2014. Okay, just I'll write it. So solution of Bessel function. Solution of this Bessel differential equation. Okay, solution of Bessel differential equation. Okay, solution of Bessel differential equation. So this is j and x. Okay, j and x. This value is this is 1 upon 2 to the power n into n factorial sigma r equal to 0 to infinity minus 1 to the power r upon r factorial into n plus r factorial e to the power this is no, not e to the power, so x by 2 to the power x by 2 to the power, this is 2r plus n. Okay, so this is 1 upon 2 to the power n into n factorial sigma r equal to 0 to infinity minus 1 to the power r upon r factorial n plus r factorial x by 2 to the power 2r plus 1. Okay, very important, and this formula is asked in CSIR NET June 2014. Okay, so very important, or this is for n equal to integer value, for n equal to integer value. Very important, guys, so you need to note down. Okay, so this is the solution of Bessel differential equation. Okay, so 1 upon 2 to the power n upon n factorial sigma r equal to 0 to infinity minus 1 to the power r upon r factorial into r plus n plus r factorial x by 2 to the power 2r plus n. Okay, now this is for n equal to integer value. If n is fractional value, then the solution of Bessel function is different. Okay, so for n equal to fractional value, okay, fractional value, then j and x is going to be x to the power n upon 2 to the power n sigma r equal to 0 to infinity minus 1 to the power r upon r factorial gamma n plus r plus 1 then x by 2 to the power r. Okay, so this is j and x equal to x to the power n upon n factorial sigma r equal to 0 to infinity minus 1 to the power r upon r factorial gamma n plus r plus 1 x by 2 to the power 2r. Okay, and here n factorial is equal to gamma n plus 1, and gamma n plus 1 value is n gamma n, right? This we know. So this is also very important, guys. So this is the, if n value is fractional, then this is x to the power n upon 2 to the power n sigma r equal to 0 to infinity minus 1 to the power r upon r factorial gamma n plus r plus 1 x by 2 to the power 2r. Okay, okay, so this is the one. Okay, and for n equal to 0, the value of j0x is this 1 to x square plus 1 upon 2 factorial 2 to the power 5 x4 plus 1. So this is the value for j0x. Okay, j naught x. Well, next point. Next point is at x equal to 0, when x equal to 0, say 0x value is 1, right? Simple. From this, if we put x equal to 0, this value is 0, this value is 0. So value of j naught x is 1. Value of j naught x is 1. Okay, and this point is j0x has zeros at x by 2.4 comma x equal to 2.4 comma x equal to 5.5, so on. So j naught x has zeros at x equal to 2.4 and x equal to 5.5 and so on. Okay, this you need to know because this question is asked in CSIR NET. Okay, this point CSIR NET point. Okay, so j0x has zeros at x equal to 2.4 comma x equal to 5.5, so on. Okay, well, next is this is also important. J and x, this J and x is oscillatory function. Okay, oscillatory. So J and x is oscillatory function. Okay, so this is oscillatory function with varying time interval, with varying time interval. Okay, so J and x is oscillatory function with varying time interval, varying time period and amplitude, varying time period and amplitude, varying time period and amplitude. So oscillatory function with varying time period and amplitude. Okay, well, so this is the oscillatory function, guys. Okay, this one here, okay, this is the one, and here this one. So this is this cuts here, right? So J naught x has zeros at this 2.4 and 5.5. Okay, this is the one, and this is J n x is oscillatory function with varying time interval and period. Okay, so these are the zeros. Okay, which cut on x-axis at 2.4, 5.5, and so on. Okay, and next point is J 1 by 2 x. The value of J 1 by 2 x is root 2 upon pi x sin x. Okay, and similarly, and the value of J minus half x is root 2 upon pi x cos x. Okay, so these are the this is about Bessel function, guys. Now next topic is Laguerre function. Okay, Laguerre function. Okay, so this is Laguerre differential equation. Okay, Laguerre equation. Okay, it is Laguerre differential equation. So this equation is the form of this equation is x d2y over dx square okay, so this is x d2y over dx square plus 1 minus x dy over dx plus ny equal to 0. Okay, x d2y over dx square plus 1 minus x dy over dx plus ny equal to 0. Okay, or we can write simplified further, so it is going to be d2y over dx square plus 1 minus x upon x dy over dx and upon x equal to 0. Okay, yeah, so here value of px is 1 minus x upon x, and qx is n upon x, right? So we can see at x equal to 0, value of px is also infinite and qx is also infinite, right? Infinite. So this makes regular singular point. Right? How we've got px infinity? I have already explained, like limit x tends to 0, px, right? So this is, we put the value. So limit x tends to 0, px is 1 minus x upon x. We'll put x equal to 0. So this is going to be 1 minus 0 upon 0, that is infinity. Okay. This is how we'll get px and qx, and those values will be infinity. Okay. So x is 0, x equal to 0 is singular point, regular singular point. Okay. Next, Rodriguez formula. Okay, Rodriguez formula. So that is Rodriguez formula for Laguerre differential equation. Okay, Laguerre differential equation or Laguerre differential equation. Okay, so that is the formula is ln x. Okay, so ln x is equal to e to the power x upon n factorial, e to the power x upon n factorial, dn upon dxn, x to the power n, e to the power x, e to the power minus x. Okay, so this is the Rodriguez formula, e to the power x upon n factorial, dn upon dxn, x to the power n into e to the power minus x. Okay, so from here we can get a value of L0, L0x or L0x, that value is 1, important thing, and L1x, this value is 1 minus x. Okay, and value of L2x is going to be x square by 2 minus 2x plus 1. Okay, x square by 2 minus 2x plus 1. Okay, so these are the formula. Now generating function, that is orthogonal condition. Orthogonal condition for this Laguerre differential equation. Laguerre differential equation. So that is going to be 0 to infinity e to the power minus x ln x into ln x. Okay, dx is going to be chronicle delta mn. Okay, so 0 to infinity e to the power x ln x dx is equal to chronicle delta mn, where delta mn equal to 1 if m equal to n, and delta mn equal to 0 if m not equal to n. Okay, now generating function. Generating function generating function is x, which is a function of xt, is going to be e to the power minus xt upon 1 minus t, e to the power minus xt upon 1 minus t upon 1 minus t. Yeah. Okay, so this is the generating function, that is equal to sigma n equal to 0 to infinity t to the power n and ln x. Okay, this one. So this is generating function. This you can get in question as well. So e to the power minus xt upon 1 minus t upon 1 minus t. Okay, that is n equal sigma n equal to 0 to infinity t to the power n ln x. Okay, well, this is the generating function. Okay, now I'll solve one question. So this question is going to be simple question. 2nx 2n plus 1 2n plus 1 x pnx x pnx equal to n plus 1 pn plus 1 x plus n pn minus 1 x. Okay, this is this we need to prove. Okay, so we'll take left hand side. So this is going to be 2n plus 1 x pnx. Okay, so we'll take and for n equal to 1, this is going to be 2 into 1 plus 1 x p1x, right? And this is, we know the value, this is 3x into pnx value is x, right? We know, I've already explained in my previous lecture, value of p0x, p1x, p2x, p3x. Okay, so 3x square. Similarly, we'll take right hand side for n equal to 1. So this is going to be 1 plus 1 pn p2x plus n means 1 into p0x. This is going to be 1 into p0x, right? So we'll put the value 2, that is 2. Value of p2x is, this is 1 by 2, 3x square minus 1, p0x is 1, right? 2 will get cancelled, 1 will get cancelled, 3x square. So left hand side equal to right hand side. Okay, this is done. Okay guys, very simple question. Next, Cauchy-Euler differential equation. Okay, so this is Cauchy-Euler differential equation. Cauchy-Euler differential equation. Okay, Cauchy-Euler differential equation. So this is this one, a2 x square dy over dx square d2y over dx square plus a1x dy over dx plus a naught y plus a naught y equal to qx. Okay, so this is the Cauchy-Euler differential equation. A2x square d2y over dx square plus a1x dy over dx plus a naught y equal to qx. Okay, well, so this is the one, how to solve this type of equation. Okay, that is the question. Okay, this is Cauchy-Euler linear differential equation of second order. Okay, so for solving this, we'll put x equal to e to the power z. From here, ln x is going to be z. Okay, and then what we are going to do, we'll say let x dy over dx, will put this dy. Okay, and x square dy d2y over dx equal to dx square, will put d into d minus 1 y. Okay, and if we put these values in equation, and then we'll be able to solve, we'll easily solve the question. How we are going to do it, I'm going to solve one question, then it is going to clear your doubt. Okay, so question is x square d2y over dx square, okay, minus 2x dy over dx minus 4y equal to 4y equal to x to the power 4, x to the power 4. So first we'll replace it, right? Let x equal to e to the power z implies ln x equal to z, and this I have already told you. So this is going to be x square d2y over dx square is going to be d into d minus 1, right? Y minus this is going to be 2 x dy is just dy, okay? X dy over dx is dy we put, right? I have already explained here. And then 4y equal to x, that means e to the power 4z x4, okay? Now we'll solve it. So this is going to be d square minus d d square minus d minus 2d minus 4 y is going to be e to the power 4z, okay? So this is going to be d square minus 3d minus 4 y is going to be e to the power 4z, okay? So this is we can see non-homogeneous equation, right? So auxiliary equation is going to be d square minus 3d minus 4 equal to 0. So this means d minus 4d plus d minus 4 equal to 0, right? So this is going to be d minus 4 and d plus 1 equal to 0. So value of dr 4 comma minus 1. So CF is going to be, we have already solved differential equation, right? So I hope you will be able to understand easily. Okay, so this is C1 e to the power minus z plus C2 e to the power 4z. So we'll convert it. This is C1 e to the power 4z means 1 upon x, right? Because we have put x equal to e to the power z from here, right? X equal to e to the power z, right? So 1 upon x, C1 into 1 upon x plus C2 e to the power 4z means x to the power 4. Okay, so this is the CF. Okay, now we'll find PI. Okay, PI. So PI is going to be that we know that 1 upon d square minus 3d minus 4 e to the power 4z, right? This one. So this is going to be, now this is going to be PI is going to be equal to, is going to be equal to 1 upon d square minus 3d. Already explained how to find PI, right? Particular integration. Okay, particular integral. So here, if you put that is a equal to 4, d equal to 4, then it is going to give 0 value. Okay, so fa is going to be 0. So that's why I'm going to do directly. So this is going to be z e to the power 4z upon, this is going to be f dash value z into 1 upon f dash, so 2d minus 3 e to the power 4z. Okay, because this putting value, it is giving 0. Okay, so this is going to be z e to the power 4z. Now we'll put d equal to 4, so 2 into 4 minus 3. Okay, so z e to the power 4z upon 5. Okay, so therefore for now we'll convert it into e to the power 4z. Okay, 4z. So this is going to be z x to the power 4 upon 5. Or z value is ln x. Okay, this is ln x, because we know x equal to e to the power z. So therefore solution is going to be CF plus PI. So this is going to be C1 upon x plus C2 x to the power 4 plus ln x x to the power 4 upon 5. Okay, so this is the answer, guys. Okay, last point is Wronskian. Okay, Wronskian, how to find Wronskian? Okay, Wronskian, sorry, Wronskian. 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 Okay, Wronskian means if y1x and y2x are two uh, solutions of a second ordered linear differential equation, second order linear differential equation. Okay, then if y1x and y2x are two solutions of second order differential equation, okay, then Wronskian W is going to be y1x y prime y2x. Okay, so this is, so the Wronskian is determinant of y1x y2x y dash y1x y dash y2x. Okay, this is the Wronskian. Okay, and next is very important. From here questions are asked in the examination in CSIR, NEET, JEE, Jest. Okay, so if here also, if Wronskian W equal to 0, that implies linearly dependent. Okay, solutions are linearly dependent. If it is not equal to 0, that implies linearly independent. Okay, solution are linearly independent. Okay, now this is if there is a formula, if so this wrong, if you have to find Wronskian W at x equal to x1, this value is going to be, this question is asked. Okay, Wronskian x equal to x naught e to the power minus px dx power minus px dx, and limit is going to be x naught to x1. Okay, this is important. Okay, so Wronskian at x equal to x1 is going to be equal to Wronskian at x equal to x naught into e to the power x naught minus x naught integration minus integration x naught to x1 px dx. Okay, very important formula. We will solve question. Okay, 12. So this is the Wronskian, right? And linearly independent and dependent is very easy to understand. If there is that is 0, right? If that is 0 or W is 0, that linearly dependent. For you can you can take example of bank as well, right? If you don't have balance, then you are dependent on your parents, right? So W is 0, so linearly dependent. You can understand from your bank balance as well. If you have balance, then you are not you are independent. If you haven't balance, then you are dependent on someone, right? Your parents. So well, so this is the linearly dependent and independent condition, and this is very important formula. That is, if you have to find Wronskian at x equal to x1, that is going to be Wronskian at x equal to x naught into e to the power minus integration x naught to x1 p dx. Okay, well guys, this is all about the class today. Okay, so guys, before ending the class, I would request the students who haven't subscribed my channel